In this question, we are asked to find all the values of k for which a given quadratic equation has two real distinct roots. We should firstly remind ourselves of the basic shape of all quadratic graphs. Firstly, a quadratic graph is either shaped like a symmetrical U shape or a symmetrical N shape. This is according to whether the value of the A is greater than 0 or A is less than 0. A nice way to recall this fact is that positive values of A look like a smiley face, whereas negative values of A look like a frowning face. And a person with a smiley face would be regarded as being positive. A person with a frown may be negative. When solving a quadratic equation, we are looking for the positions where the quadratic graph crosses or meets the x-axis. We will look at all the cases in which this can occur next. We should recall that the number of roots of any given quadratic equation is determined by the value of its discriminant, which is the value of b squared minus 4ac. When b squared minus 4ac is greater than 0, there are two distinct roots. The sketches indicate the position of the graph relative to the x-axis for both positive and for negative values of a. The highlights indicate the position of the two roots in each case. In the case where b squared minus 4ac is equal to 0, then there is one root. This is referred to as a single repeated root. The sketch indicates the position of the graphs relative to the x-axis for this case, and the highlight indicates the position of the repeated root. In the case where b squared minus 4ac is less than 0, there are no real roots to the equation. And as the sketches indicate, the graph is always either above or below the x-axis. We will now return to take a look at the solution of this particular question. Firstly, we need to collect all the terms of this equation onto one side. On doing this, we realise that there are two terms which are x terms. These have been highlighted. We next factorise these two terms to obtain a single term in x. The question tells us that this equation must have two distinct real roots. This means that the discriminant must be greater than 0. Also notice that the values of a, b and c to be used in the discriminant are the coefficients of x squared, x and the constant term respectively. We next expand and simplify this expression as indicated. This gives us a quadratic inequality, which we may notice has 4 as a common factor, and so we can simplify by dividing in all terms by 4. To complete this solution, we now need to solve this quadratic inequality. First, we notice that the quadratic k squared minus 5k plus 4 is a U-shaped quadratic. We next consider where the quadratic k squared minus 5k plus 4 would cut the axes. These values are given by the solution of the equation k squared minus 5k plus 4 equals 0. And solving this equation, we get the values k equals 1 and k equals 4. Considering the graph of this quadratic in K, we would then have the following. And as we are interested where this is positive, these are the regions indicated in red. As between the two roots, the graph is clearly in the negative region, indicated in green. And so the solution to this quadratic inequality is where k is less than 1, combined with the region where k is greater than 4. and notice how this is written. I hope that this short video has helped explain what is going on within this examination question.
Now we're going to have a look on GeoGebra at aspects of this question, and we start off with the equation rearranged to equal 0 as we did in the question. So we're going to have a look at what that looks like as a graph by looking at y equals x squared plus 2k plus 4x plus 9k. And because it has the change in k, we're going to put a slider in. And if we put the slider at 0, for example, then this is going to be x squared plus 4x equals 0. So we can put that on the screen as well. And then as we change the slider, the equation will change. Okay, so what does y equals x squared plus 4x look like? Well, we can pop that up on the screen, and there it is. And we can move k about. If we put it to -2, then we can see there are no x's, and so it's symmetrical about the y-axis. So let's just bring the slider along so we can see the whole graph. And at this point we can see that we have two roots, and we can put them on. In GeoGebra you can set various points up, and one of this points options is you click on an object and it shows you the roots. So there's one of the roots and there's the other root. And as we slide this along, we can see the roots moving. Okay, so we found in the question that we had two roots as long as k was less than 1. And we can see that when we make k equal to 1, we have just one root. Then we go between k equals 1 and k equals 4, which is the region where we had no roots. And it bounces back round, and there's our one root again when k is equal to 4. And then when we go k greater than 4, we have two roots again. So we can see that our answer is correct, and we can see what's happening with this quadratic equation. Now, one thing that's very interesting is to have a look at what's happening to the minimum point. So if we pop that onto the diagram, there it is. Now I'm just going to move it from k equals 5 down to minus something, and I want you to look at the path of that minimum point. So up it goes and then back down again. So I wonder if you've got any thoughts on what sort of path that is taking. Now one thing we can do is we can put a trace on a point. So we turn the trace on, and then with the slider we can slide back into the positive. So we'll see what happens. It looks a bit like a straight line at that point, but it's starting to curve over. And actually, that looks... Well, what do you think it looks like? Looks a bit like a quadratic, doesn't it? It's a negative quadratic. But not only does it look like a quadratic, if we put k to 2.5, which is of course halfway between the 1 and the 4, that are the sort of key numbers in this question, then it looks very much like a reflection. So if we look at the reflection of our original quadratic, then that's the reflection in the x-axis. And then if we want to see if it is the same shape as our traced out path, we can pop in another slider, and this is just going to move it up. And sure enough, it looks very much like that does exactly go through there. Now that doesn't prove it, so if you did want to prove it, then you can have a look at an algebraic method. I'll leave that as an exercise for you to have a go at. It's quite difficult, so don't despair if that's a bit of a struggle. We've connected the algebraic approach that we used in the question, although we did use a sketch there to check the region where the quadratic did have two roots, but we could have done that numerically. But of course, a quadratic, as well as being an algebraic object, is a geometric object, and we've looked at this question now from a geometric point of view. There is another way of looking at it as well, which is that if we move the quadratic about, then what we're really interested in, although when we move it we want to get past the point where we have roots, so there's our one root there and then two roots, this point here can tell us when we're having one or two or no roots. Because if this point, because it's a positive quadratic, a U shape rather than a upside down U, or an N, I think it said in the question, if this point is below the x-axis, then we're going to have two roots. If it's on the x-axis, we have one root, and if it's above the x-axis, we have no roots. So we could say in this question that if the y value of the minimum is below 0, then we'll have two roots. So we see the y value of the minimum is 0, we have one root, and then below 0 we have two. So we're looking for the y value to be less than or equal to 0. Now, since we started talking about minimums, we are moving into differentiation. So if we were to differentiate the general form of this with the k still in it, then we're going to get 2x and then 2k plus 4. So we then have the numerical version here, which relates to this green one and the actual curve we're looking at. So we want to know the y value of the minimum point. And to get that, we're first going to have to find the x value. So let's have a look at that. So there's our dy by dx. If dy by dx is 0, then this tells us that 2x plus 2k plus 4 is 0, which tells us that x is actually equal to minus k plus 2. And there's a step missing there if you want to fill it in. So that means the x value of the point A, the x coordinate of the point A, is minus k plus 2. So that's the x value of the minimum point. And now we need to work out the y value, because that's the one we need to test to see if it's above or below the x-axis. So if we put this value for the x into the original equation, that's x squared, so that was going to be minus k plus 2 squared, then 2k plus 4 times x, so 2k plus 4 times minus k plus 2, and then add our 9k on. And you can have a go at the algebra if you fancy, but if you tidy that up, you end up with minus k minus 1, k minus 4. Which is the same, pretty much, as what we got in the question. And so we can say that the point A is equal to this. Now, we could write this out further, but I'll leave that as something for you to do. But what we can see is, from here, that if k is greater than 4, then this bracket will be positive, this bracket will be positive, this will be negative, and therefore if we go up to above 4, our turning point will be below y equals 0, so below the x-axis, so we'll have our 2 roots. On the other hand, if k is less than 1, then this will be negative, this will be negative, so we've got a minus times a minus times a minus, which is minus. So if we go to below 1, then again our turning point is below the x-axis, giving us 2 roots. And then if we think about a number in between 1 and 4, well, between 1 and 4, this will be positive and this will be negative. So we'll have negative times negative, which is positive, and sure enough, the turning point is above the x-axis. Now, this is not a recommended way to do the question, because as you can see, it's a bit more fiddly really than the method shown in this video. What it's showing you is how different parts of mathematics connect together, and it's rather lovely that when we solve using the quadratic equation and the determinant and the b squared minus 4ac, we end up with the same expression as we do when we approach it through calculus or differentiation and looking at the turning point.